Okay, hi guys. Today we are doing electrochemistry. So I'm just gonna recap what we did yesterday first, and then by the end of today's lesson, you should be able to do EMF as well as explain the different applications of electrochemical cells. So we got to this question yesterday, and then we couldn't do it because we ran out of time. So we're quickly gonna do it now. So they tell you for zinc and gold oxide. Oh, and then they give you a formula for gold oxide, which is Au2O3, silent solution of potassium hydroxide. Determine the oxidation and reduction half reactions, the overall balanced chemical equation, and the standard cell notation for the cell. So, let me just get my whiteboard. So the first thing that you have to do is you're going to have to write down what you have. So they're telling us about zinc. So you've got zinc. And then we have our gold. So I am just going to quickly go to my document and show you. This is the formula sheet on a past paper. Okay, so we are using the standard reduction potentials. And if I go and look on my paper, if I search for zinc, okay, I find it down here, and it has a value of negative 0.76 volts, whereas your gold, which is Au, if you go and look for it, has a value of plus 1.5. It should have a value of plus 1.5. But it's going to be up here. So what you should see from it is that your zinc is going to be the one that is going to undergo oxidation. So it is the one that wants to lose electrons. So if we go back to this reaction that I was busy writing, then the zinc is going to go from a solid state to an aqueous state. Because it has that negative value. And your gold is going to go from an aqueous state to a solid state because it's going to gain electrons. So this is my reduction reaction. This is my oxidation reaction. And once you have identified them, we can write our overall reaction by multiplying with the same number of electrons for each side. So here I've got 3, and here I have 2. So the only thing that you do is you're going to multiply the top reaction with 3 and the bottom with 2, because they don't have another factor that can go into both of them. So overall, the reaction would be 3 solid zinc plus 2 aqueous gold solution ions will give you 3 zinc ions plus 2 gold ones in its solid state. Okay, but then just going back to the question, they told us that it is in a solution of potassium hydroxide, and they tell you that the gold is in the form of gold oxide, so it is bonded to oxygen. So you have to remember to put that oxygen back into your equation because that's just one of your spectator ions. So you will have an oxygen for this gold molecule and an oxygen over here. So if you rewrite this formula, it'll be 3 solid zinc molecules plus your gold oxide, and you see that I've got 2 golds there and I've got 2 there, so I haven't really changed anything. It's just in a different form, which is an aqueous phase. And then I've got 3 zinc molecule ions plus, sorry, that's my mistake. My zinc is now going to bond to my oxygen, so I've got zinc oxide now. And if you remember, over here you've got 3 oxygens, and now I've got 3 oxygens as well. So that doesn't change. Plus I have 2 silver in its solid state. Okay, so that's your overall reaction. And then when we write it in our cell notation, we have to remember that cell notation starts off with the anode and it goes to the cathode. Okay, and you remember the little rhyme, an ox gets fat and red cat gets fat. So your anode will have the oxidization reaction. So you'll say your Zn solid species, indicate the phase change, your Zn ion, put the salt bridge in between, then you have your gold oxide, an aqueous solution, electrochemistry, phase change, and you have your, oops, and no one has picked up that I've accidentally written silver twice. The gold solid. And that is cell notation. Okay, so does that make sense, everyone? We know how to do cell notation. You just need to be able to identify your anode and cathode, and that is explained by knowing which one is oxidized and which one is reduced. Okay, then the next thing that I was starting to explain yesterday is EMF. So EMF is just the potential difference in your cell, the maximum potential difference in your cell from your 2 electrodes in the half cells. And we can use 3 equations, and they're basically the exact same equation. We're just writing it in a different way to work it out. So what you would do is to find your EMF, which is just this electron potential for the cell, is equal to the reduction half reaction value minus the oxidation half reaction value, or it is just the oxidizing agent half value minus the reducing agent value, or it's the cathode value minus the anode value. And as you will know, reduction occurs at the cathode, which is your oxidizing agent, and oxidation occurs at the anode, which is your reducing agent. So it's the exact same formula written in 3 different ways. And we get these values from our table. So I'm going to do some examples because that is the easiest way to understand it. And so the first one says a cell contains a solid lead anode in a gold ion solution. Represent the cell using standard notation, and then 2, calculate the cell potential of the electrochemical cell. So I'm just going to find this one on my whiteboard. Okay, so they tell you you've got your lead anode. So they've told you which one is being oxidized. And then you've got your gold ion solution. So then you can go and start off. Lead is Pb. And if it is oxidized, it means that it is going to go from its solid phase and lose an electron. I just wrote that the wrong way around because I've run out of time. Into electron. And if we write that in cell notation, we will start off with lead as a solid, phase change indicated, and then write lead as an aqueous species. and give your salt bridge. And then for your iron, you've got a gold iron solution. In this case, it would most probably be Au3+. Okay, so you start off with an iron, it will gain electrons, and it will become a solid. And so if you were to write it in your thing, you would say Au3+, indicate that it is aqueous, write the phase change, and then show that it becomes a solid. That is the one that occurs at your cathode. So that was easy. That you got from here, knowing that lead is your anode and gold is your iron solution. So if lead is the one being oxidized, then the other one has to be reduced. And so you're going to go from anode to cathode. So you just write the anode bit and then the cathode bit. Remember your phase changes and your salt bridge. Very important, remember your phases of each species. Then, so this was one. Then the second bit, they ask us for cell potential. So now we are going to use our table. And I can just show you it again. So from the table, your PB, your lead, is over here. Okay, it's got a value of negative, I'm just going to write it next to that reaction, negative 0.13 volts. And then your Au isn't on your reaction sheet, but I know it's got a value of 1.5 volts. So just next to it, write positive 1.5 volts. Okay. Then we're going to write the formula. So I like using the formula E Sol is equal to E cathode minus E anode. My cathode is the reduction one. It's this value, so it's just 1.50 volts minus negative 0.13 volts. And that gives you an overall value of positive 1.63 volts. Remember yesterday I said that if it's a positive value, it means that it is spontaneous. So this is a chemical reaction that will just occur and you can actually produce a battery out of it. If it was a negative value, it would be non-spontaneous. Okay, so that was the one example. The second example, they tell you that will copper react with dilute sulfuric acid, you are giving the following half reactions. Then they give you the copper half reaction and they give you the hydrogen half reaction and the values for it. So the first thing that you should realize, this over here has a positive value, which means that it would be oxidized. And if this one is oxidized, then this would automatically be reduced. Okay, so when you then write your things in half reactions, you write copper, solid, because it's being oxidized, will go from a solid to an ion plus 2 electrons. And then your hydrogen will go from its proton form, so an ion, aqueous, plus 2 electrons to a gas. This one, you can actually use the formula because they have given it to you, or you have figured it out in terms of it being oxidizing and reducing. You can say E Sol is equal to E reduction minus E oxidation. And then you just plot your values in. So my reduction is 0.00 volts minus 0.34 volts. You get a value of negative 0.34 volts. And so this means that it is non-spontaneous. So you would actually have to put a current through the system. It wouldn't happen if you just added them together, non-spontaneous. So then your answer would be, no, they won't react because of the fact that it's a non-spontaneous reaction. Then right next to it, there is another little question, and it says, will zinc react with dilute hydrochloric acid? And you are giving the following reactions. So then they tell you what zinc is, and they tell you what hydrogen is. And I know that zinc is a metal. That is in my second period. So no, sorry, I'm wrong. It's only my second period. Zinc is one of your more reactive metals. Okay, so zinc is going to be the one that oxidizes because it wants to lose electrons. And this is going to be the one that will be reduced. Okay, and when a metal and an acid normally comes together, they should in theory give you this hydrogen gas, but only if the metal is reactive enough. So what we're going to do is we're going to say E of my Sol is equal to E reduction minus E oxidation. Whoops. And you can plot that in there. So you've got 0.00 volts minus negative 0.76 volts. And so these two will make a positive, and you will have a positive 0.76 volts. And so seeing this positive, it is spontaneous. So if you were to throw them together, they would react because of the fact that it is spontaneous. So do you see how to use it? If they give you it in anode and cathode form, you can use the formula that says anode and cathode. If they give it to you in reduction and oxidation, you can do it in reduction and oxidation. And if they tell you it's a reducing agent and an oxidizing agent, you can use the other one. Does that make sense to everyone? If they don't, so I didn't write it for the second one, sorry, because they didn't specify it in the question. It is a good habit to do it, but if they don't specifically ask for it, you don't have to. That you're just being asked to say whether it's spontaneous or not, which means you have to use the formula. The top one, though, they did specifically ask for cell notation, and the only way that you can normally work it out is by showing how you got to the steps of understanding which is reduction and which is oxidation. So look at your mark allocation. If it's a lot of marks, just make sure you write everything in there. If it's 2 or 3 marks, don't worry about it. So then what we're doing today is we are looking at the application of electrochemical cells. So yesterday we looked at galvanic cells, and I told you that they could be batteries. And that is basically what all you do with a galvanic cell is we use them for different batteries. So I gave you 3 examples over there. You can use it for a camera battery, which is lithium, or they can be used in hearing aids. Then they use silver oxide, and in watches, they use either silver oxide batteries or mercury batteries. For you guys, though, they don't expect you to have an in-depth understanding of how the battery actually works. What they do expect you to know is actually the electrolysis side of it. So we're going to look at electroplating, the chloralkali industry, and aluminium extraction. So the first thing is electroplating. And electroplating is basically just a process by which you put a current through a liquid that is made up of some form of a metal, and then that metal will go and form a thin layer on top of another metal or another object. And so it is normally done to protect your other metal from corrosion, to make things, to give things a wear resistance, or just to make jewelry. So you get gold-plated jewelry or silver-plated jewelry, and it's cheaper than buying the real thing. So it's kind of like a mass production thing. And so the big application of it that you specifically have to know is called electrorefining. So electrorefining is really important because this is how we get copper out of the earth. And by now, I'm hoping that you know copper is one of your most conductive metals. And they are very, very important for especially our electricity and using them in our wires for electricity. So what happens in electrorefining is basically just a large scale of electroplating. And what you do is you would take impure copper out of the earth and you would put it through this process where you let a current run through it, and then the copper will be extracted out of the rock and be put onto an electrode, and it will form a pure copper. So I'm going to show a picture which explains it easier. So what happens is you've got your impure copper on the anode side, okay? And when it's impure, it just means there might be some iron in there might be some silver in there, any other metal that you can think of, or any other substance you can actually think of can be in there. And then they run a current through this, and as they run the current through this, electrons are extracted out of the impure copper, and it goes through the system. And as the electrons are being extracted, your copper falls off as an ion. That ion then moves to the other copper, which has the pure copper on it. And so when the electrons get to the pure copper side, this little copper with the 2+, the ion, takes up those electrons, and they go and sit as a precipitate on the pure copper. So this impure copper will get thinner and thinner, the electrode, and the pure one will get thicker and thicker. And then you would take out that pure copper and put it through a process where you heat it up and then make it whatever you want to make it. Does that make sense? So you need a current to go through the system, and that current causes electrons to be pulled out of the impure copper. Those electrons cause the copper to drop off of the electrode as an ion. That ion then swims to the side where the pure copper is an electrode. And then as soon as the electrons come, they bind to those electrons and they precipitate onto the pure copper side. And you generally get about a 99.99999% pure copper. Make sense for everyone? Yes, no, maybe? Okay, cool. So then the next part, and probably the most important part, is the chloralkali industry. And this is basically how we take brine, which is a salt, and we make it into chlorine, hydrogen, and sodium hydroxide. And then sometimes you get byproducts of it, like sodium chlorate, which is actually bleach, and chlorate and chloride ions, which you don't want. So I'm going to explain it using my whiteboard. Okay. So this is how it works. Let's say I have my electroplating thing here. Okay. And I've got my, I've got my anode over here. And I have my cathode over here. And in the solution, I have water and I have my brine or my salt, which is sodium chloride. And what happens is you run, I've got my battery in there, you run a current through the system. And when you run a current through the system, what you would see is these little gas bubbles. Those are my gas bubbles next to my anode and next to my cathode. Okay. And so what you're actually getting is you're getting chlorine gas and you are getting hydrogen gas. And one is going to go to the positive side anode, and the other one's going to go to the negative cathode. Can you guys guess which one is which? Ideas? Anyone? Okay, so where is my H2 plus? So H is positive, yes. So which one is it going to go to? My positive or my negative one? Okay. So I'm going to break it down this way. Imagine you have your anode over here, and my anode is positively charged. When my current was put through my water and my brine, you get your water to break up into positive protons and hydroxide molecules, and you get your salt to break up into sodium and chloride. Okay, so what's going to happen is my chloride is negatively charged, so is my hydroxide. They're both going to be attracted to my positive anode. On the other hand, my cathode is negative, so my positively charged sodium and my positively charged hydrogen or my proton is going to be attracted to my negative cathode. Okay, what happens is when you're, I'm just going to erase this because it looks a bit crazy. When your chlorine or chloride ion gets to this positive charge, what happens is it gives its little electron to this electrode. And when two of them has given an electrode, they bond together because chloride is diatomic, and you get your little chlorine gas. So the gas that's going to be around my anode is chlorine gas. Because I had my chloride ions that was attracted to my positive anode, it gave up its electrons and it formed chlorine gas. Then on the other side, let's just take a different color, okay? What's going to happen is you now have electrons coming in here. Okay, those electrons coming from the chlorine is coming in here. I have my sodium and my hydrogen protons standing here. What happens is that your protons are much more reactive than your sodium, so they grab up this electron. And in this process, when they grab up an electron, they can then go, and they are also diatomic, they can bond together and they form proton gas, hydrogen gas. So now, let's say the blue dots next to my negative cathode is hydrogen gas. What ends up happening is, because you still have your OH negative over here and you have your Na plus, okay, those two are going to come together and they will form your sodium hydroxide base. So they bond together to form a base. Your protons come together to form a gas. Your chlorides come together to form a gas. And this is the products that you want out of this process. We then use the chlorine gas to make a bunch of products that needs chlorine, and we use the protons for whatever we can use them in reactions, and your sodium hydroxide, that base is its reactions. Does that make sense to everyone? Okay, so this was in theory what's supposed to happen, but then there's a few problems that end up happening. And so we have kind of gone and refined this industries. So to overcome this problem, the chlorine and the sodium hydroxide must be separated from each other. So what you don't want is when you have that chlorine gas and your sodium hydroxide, they can bond together and they can form things like sodium chlorate or bleach or things like that, and you don't want those byproducts. So what we have done is there are 3 ways or 3 cells that you can use to separate them. And in theory, I've seen that you guys need to know all 3, and there has been a question or 2 about them. So the first one is a Mercury Sol. So what ends up happening is your brine, which is sodium chloride, gets pumped into your system, okay? When it's pumped in here, a current is run through it. When the current runs through it, you release chlorine gas here at the top. And then what happens is you have this mercury over here. Okay, remember mercury at room temperature is a liquid. So when you now separate your sodium and your chlorine, the sodium will go and it will form an amalgam with your mercury. Okay, that amalgam then goes and it flows down this tube and into another vessel. And in that vessel, we can then separate the mercury and the sodium from each other using water. So the amalgam comes in here, water is pushed into the system. Water then causes a reaction to happen so that your OH negative bonds with the sodium and you form your sodium hydroxide, and your OH negative, if it splits from your water, you've got H plus. So they will come together to form your hydrogen gas, and then your mercury can be recycled. And so this mercury can be pushed into the main vessel again. The NaCl can be separated into chlorine gas. The sodium can become an amalgam with your mercury again. They can go down to the second vessel. There, your sodium and your mercury get separated using water. You will get sodium hydroxide and you will get hydrogen gas, and your mercury is recycled. And that process just happens over and over again. Does that make sense? Do you understand the process? Okay. So this is the one way you can do it, but there are a few advantages and disadvantages to it. So the first disadvantage to it is that mercury is very expensive. It's in the industry. So this is at chemical companies, Carlos, they use these cells. So they're very expensive, and obviously mercury is super toxic. And so your problem is if some of the mercury was to bind with your brine or something like that and escape into the system, you have a bit of a problem in terms of toxicity. The other problem with this cell is that it requires a lot of electricity. So that's part of why it's very expensive. And then the other thing that can happen is your chlorine gas isn't necessarily as pure as it should be. And your sodium hydroxide doesn't always form as greatly because of the fact that your mercury doesn't always separate that well from your sodium hydroxide. So you've got mixtures between your gases and things like that. So that's the negative side of it. And then it becomes a very big problem in terms of persuading the public that it's okay to have these plants when your mercury is leaked into rivers and things like that. So the Mercury Sol is a way of doing it, but they have kind of moved away from it. And so one of the cells that they use instead is called a diaphragm cell. So in a diaphragm cell, you start off with your sodium chloride solution, which is your brine again, okay? And there's a current passed through your system, and it separates the chlorine and the sodium from each other. But you now have this little porous diaphragm over here. And what happens is that your negatively charged chlorine will move to the anode, and your positively charged sodium will move to the cathode. And at the cathode, you also have water being pumped into the system. And so your sodium can bond to the OH negative, and you will have your two gases as well. Your sodium will be pumped out. And so it looks different because you now have this diaphragm, and through this diaphragm, only the sodium can move. Does that make sense? Do you see the difference between this one and the previous one? Yes, no, maybe. Okay, cool. So this one has the advantage that it doesn't contain the toxic mercury, which is cool, and it uses less energy. But the problem is your sodium hydroxide isn't very concentrated, which means it's not very pure. And in your chlorine gas, you can often find some oxygen in between there because of the water that was also on the anode side. And so it becomes less cost effective because you have to take your product and run it through another process to purify it even more. So the diaphragm one is better in terms of the environment, but it becomes more costly because your products aren't as pure as they should be. So then we get to the last one, which is your membrane cell. And your membrane cell is probably the best one out of all of them. So what happens is, the only difference here is you now have a membrane that is ion selective. And what it means is that your cations can pass through here, but your anions can't. So based on what the charge of they are in the Google Drive, Zanzi. Based on what your charge of your ion is, it will be able to pass through or not. So you take concentrated sodium chloride solution, okay, which is a brine, you will push it into the system. As usual, your NaCl will break up, your sodium will pass through the membrane because it is positively charged, and it will move towards the cathode side. Your chloride will stay on the anode side, it will form the gas like it does, and then your sodium will bond to the hydroxide to form sodium hydroxide, and your proton that is left will form hydrogen gas. And so the only difference here is you've got this really cool membrane that is very selective, and it will only allow positive charged ions through. In this case, the only positive charged ion that you have is the sodium. So the sodium will go through, the chloride will not go through, and hopefully the process runs to completion. So the advantages for this one is you get very pure substances. The reason being that because of this membrane that separates chlorine and sodium, you ensure that there's 100% split between them, okay? And your hydroxide, your sodium hydroxide will normally have quite a high concentration because it's one of the only positive things that your hydroxide can bond with. It uses the least electricity of all the other processes. So it is much cheaper to operate. And then just like with the previous one, it doesn't contain any mercury or asbestos. So it is your most environmental friendly process. So if they ever ask you a question, which one of the three you would choose, just say the membrane cell, the reason being it's environmental friendly, uses the least electricity, and is the cheapest one to run. Then another process that is very important that you need to know is the electrolysis of, and I never know how to say this word, bauxite, which is where aluminium is found in, okay? So bauxite is found in the earth. It looks like rock, and you've got your aluminium in there. And what happens is, and I'm just going to put on the picture because it's easier to explain. What happens is you take this bauxite and they melt it. But the problem with melting bauxite is it's got a very, very high melting temperature. It's about 2000 degrees Celsius. So what they do is, instead of taking the bauxite alone, they add this thing called cryolite to it, which is also a molten form of aluminium. And the cryolite then reduces the melting point that you need. Okay, so think about this in terms of energy. It's reducing the energy that you need to let this process happen. And so what will happen is both your cathode and your anode, so these are your little anodes, the three things hanging here, are made up of graphite. And graphite is made up of carbon. Okay, it's a form of carbon. So what will happen is when you run a current through the system, your bauxite, which is normally aluminium oxide, will be separated from the oxygen. So the aluminium and the oxygen will be separated. The aluminium is positively charged because it's a metal. So it will go towards the cathode, which in this case is here. So it will sink to the bottom, okay? And then your oxygen will move up towards these positively charged anodes, okay? The aluminium is then a liquid that you can like tap out through this little angled pipe thing at the bottom on the right-hand side. But the oxygen will go and it's going to bond with the graphite. And what you form is carbon dioxide. So after a few times of doing this, what ends up happening is you burn away the anode graphite, anode electrodes. So you have to replace them regularly, which makes this process very, very expensive. So I'm just going to quickly bring my whiteboard just to make this easier. Okay, so just to quickly explain it again, you have your thing in there. Okay, so over here you've got your three anodes. They're positively charged and they are made of graphite. And graphite is just a form of carbon. Then your cathode is in here, which is negatively charged, and it is made up of graphite as well. And then in here, you've got your aluminium oxide and you've got your cryolite. When you put a current through this, you separate your aluminium and your aluminium becomes 3+ charged and your oxygen is 2-, okay? This aluminium sinks to the bottom over here, okay, as a very hot liquid. When it becomes like a lot of aluminium liquid, you can tap it out through this pipe over here. The problem is these oxygen ions go and they bond with the carbon over here. So they form gas as CO2. And every time they bond with a carbon, they are slowly but surely breaking down the anode. So it's becoming smaller and smaller and smaller. So that means this is very expensive because you have to replace it regularly. And then, like I was saying, because aluminium oxide has such a high melting point, we add cryolite to it. Does that process make sense? What I just explained? Okay, awesome. So hopefully by the end of this, you are able to explain and define electrolytic and galvanic cells. You can calculate the EMF and you can explain the applications. This is one of those topics that you really just need to go sit and study the theory. Okay, so please, please, please go and do that. You can use my slides, it's on the Google Drive, you all know that. And just read through your textbook a few times. Tomorrow we will be doing past papers, so make sure you are there tomorrow. See you guys tomorrow, same time, same place.